Okay, so far we have been using NPV, present value of net social benefit, to judge whether a project is efficient or not. So we calculate the NPV, the present value of net social benefit, and if it is a positive figure, if it is positive, we conclude that the project is efficient. In doing so, you want to realize that we are actually applying the Cauchy-Hicks criteria. In addition to these NPV decision rules, there are also alternative decision rules, and this is what we want to look at today for this topic. Broadly speaking, we can classify all these decision rules into two types, two categories. First one, those not based on discounted net social benefit. And second one, those who are based on discounted net social benefit. And each of them have their own advantage and disadvantages. But usually we will prefer the second group. Okay, the first one, payback periods. It is the length of time required for a stream of net cash returns to equal the initial cash outlay. So the idea here is that, okay, suppose I invest $10. How many years, how many periods do I need in order to get back my $10? Okay, get back my initial capital outlay. Frequently, some firms, usually particularly small firms, we can use this as a shorthand. And here the decision rule is to choose the project with the shortest payback periods. And usually we can have a payback period of less than 5 years. Let's look at examples. So suppose we have two projects, A and B. Project A, initially there's $10,000 cash outflow, and similar with project B. So they have same initial investment. And the cash inflow pattern look like this: 2,000 in year 1, 3, and year 2, 4, and year 3, 5, and year 4. Okay, the total net benefits add this up. We get 14,000. For project B, initially year 1 there's cash inflow of 5,000, year 2 2,000, year 3 3,000, year 4 3,000, and total benefits we can calculate. Sum all this up is $13,000. And for project A, how many years does it take to recover this $10,000 initial investment? So we need a year 1, year 2, and year 3. So now that's 9,000. So we need year 4. The payback period for project A is 4 years. We need 4 years to recover our $10,000 initial investment. For project B, let's calculate the payback period. So how many years do we need in order to recover this $10,000 initial investment? We need year 1, year 2, year 3, and then we get $10,000 back. So payback period for project B is 3. And if we are using payback periods as the decision rules, we will conclude that project B is better than project A because it has a shorter payback periods. But it should be clear, it is clear that actually project A give you a high level of total benefits and total net benefits as well. So here's the problem with the payback period decision rules. First, it ignores total returns, as we see it in examples. Okay, and the discounting there, or actually you can say that there's no discounting at all. It involves a very crude form of discounting, and it does not quite sufficiently include the cost of capital. Okay, for example, it might be project A, you have to finance from, say, borrowing from bank charge you the cost of capital of a loan rate of 8%. In contrast, project B, you can finance from, say, issuing bond, and the rate of return or the cost of capital for project B of 8%. And this is not accounted for in these payback periods. In addition, it contains no theory as to how to determine the minimum acceptable payback period. Well, we are going to say that, okay, we want to have a cutoff of 5 years, but there's no theory associated with this. But it does has a good, it does has a merit here. It's easy. You can use it as a shorthand. Right. There are 4 criteria based on discounted net social benefits. One is NPVs. That's one we are using. Second is benefit cost ratios. Third one is internal rate of return. Fourth one is net terminal values. So NPV is the sum of discounted value of net social benefit. So we are going to accept a project if we compute a positive NPV and reject if it is negative. So NPV is the present value. This is present value of cost. This is present value of benefit. And the cash flow that look like this. So there's benefit 1 in year 1, benefit 2, benefit 3, so on and so forth, and benefit N. And there's also scrap value in year N. So that's cash inflow. Cash outflow, there's initially cash outflow C0, C1 in year 1, C2 in year 2, C3 in year 3, Cn in year N. So this is very general cash flow patterns. And we discount all this back, so on and so forth. And same for the benefit, items of benefit as well. So we get this NPV. Let's look at examples. Okay, so here's one project, lasts for 4 years. Benefits is this, cost is this. So we can calculate net benefit for each year, and cost is negative. We put negative because it's a cost. Okay, and net benefit of year 1 is 25,000 minus 20, so it's 5,000. 24 for year 2, 35 minus 2, 33 for year 3, and 32 for year 4, and then discount it back. So discount it back. So for the $5,000 in year 1, the discounted value is, the present value is 5,000 times 1 plus discount rate, which is 15%, raised to the power of -1, and that's 4,347.83. Similarly, for second terms, third terms, fourth terms, then add all this up, we get an NPV. Sum them up. And that's $2,489.42, and it is positive. We conclude that this project is efficient. Right. So we are going to undertake this project if we got a positive NPV. That means present value of benefit is bigger than present value of cost. Divided both sides by present value of cost. So we get a present value of benefit over present value of cost is bigger than or equal to 1. And we call this benefit cost ratio. So that's the second decision rules that we can use, benefit cost ratio. And we are going to say, okay, this project is efficient if the benefit cost ratio is bigger than or equal to 1. Let's look at examples. Suppose present value of benefit is computed as $88,413 and present value of cost is $60,000. Then should we undertake this project? Okay, let's compute benefit cost ratio. 88,413 divided by 50,000. We get 1.47. So which is greater than 1. So the answer using this benefit cost ratio decision rules, we are going to say that this project is good. We should do this project. Right, okay, you want to note here that with no capital rationing, NPV, which means we have sufficient capital to undertake all efficient projects. Then in this case, NPV decision rules and benefit cost ratio decision rules will give you the same results. So if we get a positive NPV, that implies benefit cost ratio will be bigger than 1. Or if benefit cost ratio is bigger than 1, this implies that NPV will be greater than 0. One advantage of this benefit cost ratio is that it gives you a measure of rate of return. Okay, so for example, previous example, we compute a benefit cost ratio of 1.47. Then you can think the associated rate of return will be 47%. Okay, so or in other words, if you invest $1 into this project, you get 47 cents rate of returns back, or rate of return is 40. You get $1.47 back, and the implied rate of return from this project, investing in this project, is 47%. Okay. However, it has no measure of the level of the benefit, the total level of the net benefits to the society. If we are faced with capital rationing, that is, we do not have enough sufficient capital to undertake all efficient or desirable projects, and we can end up in having different results. For example, let's look at these two projects. Project A, present value of benefit is 50,000. Present value of cost is 40,000. In contrast, Project B has a present value of benefits of $10,000 and present value of costs of 5,000. Okay, it's easy to calculate NPV. 10 for A, 10,000 for A, 5,000 for B. And also benefit cost ratio 1.25 for A and 2 for Project B. So if we do not have sufficient capital to undertake both projects, and if we are using NPV, we are going to conclude A is better than B. Okay, we should do A is better than B using NPV rules. If we use benefit cost ratio rules, we are going to say that B is better than A. So we end up in having different rankings. Okay. So it's clear from the table that A has a high total level of net benefit, in contrast, B has a high rate of returns. Okay. Right. The third rule is called internal rate of returns. So previously, and when we calculate the present value of benefit, present value of cost, or NPV, present value of net social benefit, then I hope you appreciate that the discount rate that we use, the level of discount rate we use, will affect the final NPVs. Okay, or in other words, the NPV is a function of the discount rate. So in such cases, it's a continuous function, to be more precise, of the discount rate. So in such situations, then naturally we will guess there might exist at least one level discount rate such that NPV is equal to 0. Okay, and we call this rate internal rate of return. IRR is the discount rate that makes the present value of benefits equals the present value of cost, or NPV is equal to 0. Equal to 0. Okay. So when we use IRR, the decision rule is we will undertake the project if we have the IRR, internal rate of return, higher than the required discount rate or cost of capital. Then we will do this project. We judge this project is efficient. Okay. For example, say I want to build a bridge on Lost Rivers. Okay, and I compute the IRR to be 8%. And in order to finance these bridge projects, I go to bank, borrow from bank. Bank charge me 6% loan rate, and I'm going to compare this 8% IRR with 6%. Because 8% is higher than 6%, I conclude that this project is efficient. We should do it. So IRR is the discount rate that makes the present value of cost equal to the present value of benefit. Okay. And by the way, you want to recognize that this equation is high order up to n polynomial function of R. Okay, and solving these equations is non-trivial. Right. So here's examples. I'm going to just tell you that the IRR associated with this project is roughly 26.24%. Later in the second videos, I'll use Excel to illustrate the computation of IRR. And one problem is that IRR calculations might have more than one solutions to the equation of NPV equal to 0. Okay, and here's the examples. And again, I'll illustrate this in the Excels and the second videos. Okay, so if we have n changes in the sign of net social benefits in each year, then in principle we can have up to n solutions, n levels of IRR, n solutions to the equation of NPV. You consider we have n solution to these equations. When we have these situations, there's no simple solutions to these problems. We don't know which level of IRR we should use. Despite that, in practice, it might rarely occurs. All right, that's IRR. The last one, the last decision rules we can use is called net terminal values. So let's think about NPV, net present value. So for when we calculate NPVs, what we are doing is we actually discount all future dollar back to present time so we can compare them. So we are comparing apples with apple, not apple with bananas. In light of these NPV calculations, well, I hope you agree that we can also equivalently, we can also push all dollar values into the year end when the project finished. And that's what net terminal value is doing. Okay, the NTV, it is the sum of future values to the end of the projects of all benefits and costs. So here we push or we compound all present values into future, all values into futures. Okay, so we compare the dollar values at the end of the project in year N. And again, there we are comparing apple with apples, not apple with bananas. Okay, so NTV, net terminal values. So the decision rule is similar to NPV. We are going to say that a project is efficient if the NTV is positive. It's inefficient if the NTV is negative. Okay, and by the way, in doing so, we are also applying implicitly the Cauchy-Hicks criteria. Okay, NTV is equal to future value year-end value of benefits. Okay, so year 1 benefit compounded until to year N, year 2 compounded to year N until year N billion dollars, which is already year N dollars. Okay, and similarly, this is present future value of year N of costs. Right, let's look at an examples. Now we have a project of 5 years. At year 0, we need to invest $65,000. Year 1, 25, there's a benefit. Year 2, 24. Year 3, 27. Year 4, 26. Year 5, $32K, $1,000. Okay, and we are going to use a discount rate of 13.16%. Okay, and we want to calculate net terminal value of these projects. So year 5, let's end the project. So $32K, $32,000 is already terminal values. So we don't need to compound it. Okay. Year 4, $26K is year $4. This compounded to year 5, so it's 26 times 1 plus the discount rate, 13.16%, raised to the power 1, and that's 29.9. Similarly, for 27K here is 27 times 1 plus discount rate, 13.16%, raised to the power 2, so on and so forth. Okay, and add sum all this up, sum all this term up. We get an NTV of $57,152.23, and it's positive. Then we conclude that this project is efficient. All right. So here in NTVs, so we are pushing all dollars to the end of the project. Equivalently, we can think more broadly. We can also push all dollars, say, into year 2, right? So push into year 2, year 2, year 2, year 2, year 2. And essentially, we will get the same results. Okay. Right. In practice, the generally accepted practice is to use NPV. However, researchers also do sometimes include IRR, internal rate of return, and benefit cost ratios for specific purposes and because they are often better understood by the clients. And when we are assessing, evaluating projects, different projects, there exists a relationship among these different projects. Projects could be independent of each other. So there are those where the acceptance or rejections of one project has no effect on the benefits or costs of another. For example, a bridge in Sydney and a bridge in Townsville. So reasonably, they do not affect each other in terms of benefit and cost. Sometimes projects can be dependent on each other. It means that the acceptance and rejections of one project affect the benefits or costs of another. For example, a combination of shops and accommodations on the same site, then the project of shops and the project of accommodations, they affect each other. The benefit and costs affect each other. Sometimes projects could be mutually exclusive. There are those projects where undertaking one excludes undertaking another. For example, two proposals to use the same piece of land. And this is an extreme form of dependent projects. Right, so when comparing these projects, independent and mutually exclusive projects are easiest to analyze. So with independent projects, we just undertake all projects with positive NPV. Okay, if a project has positive NPV, it is efficient, we should do it. Okay, if these projects are mutually exclusive to each other, then we want to undertake the project with the highest NPV. So here, you want to be careful, okay? So now you need to make sure that these mutually exclusive projects, you need to adjust for the time frames, okay? Different time frames, okay? So like we in previous topic, we talked about the rolling over the shorter periods projects or equivalent annual net benefits. Okay, you want to be aware about this. With the dependent projects, so now you have to consider NPVs of combination of projects. Okay, the idea here is that, okay, rather than treat these projects separately, combine them into one and choose the combination which has the highest NPV. Right, okay, here's a final comment. Most analysis and policy discussion concerning the environment versus development assumes that the development and environmental protections are mutually exclusive. You want one, you have to give up the other. But this is often wrong. Here's an example. A mine development, mine results in roads being built into an area, and this might lead to tourism and protection of the environment from pests and weeds, etc. That was taking place when the area was grazed. Okay, in such cases, it could be they can actually complement each other. All right, this is the alternative decision rules.